What if something out of the ordinary is happening to Earth and most people are barely noticing it? Our planet is not breaking, but it may be changing in ways modern civilization was never designed to handle. The real danger is our fragile systems, built on perfect stability and predictable natural rhythms. As scientists track unusual signals, one question grows harder to ignore: can humanity adapt fast enough? In this video, we explore the planetary changes that could challenge our future. Now, let's begin. On June 29, 2022, something happened that no textbook had prepared us for. Earth finished a complete rotation in 1.59 milliseconds, less than 24 hours. Not a rounding error, not a sensor glitch, a confirmed, verified, world record-shattering measurement, the shortest day ever recorded since atomic clocks first came online in the 1960s. Scientists at the International Earth Rotation and Reference System Service, the global authority responsible for tracking exactly how fast our planet spins, confirmed it without ambiguity. And just like that, the most basic fact you were ever taught a day has 24 hours quietly stopped being true. Think about everything in your life that runs on a clock: your alarm, your calendar, your flight departure time, the timestamp on every email, every bank transaction, every text message you've ever sent, the traffic light cycles, the hospital medication schedules, the GPS telling you to turn left in 300 feet. Every single one of those systems rests on a single, invisible assumption that Earth completes one rotation in exactly 86,400 seconds. No more, no less. This assumption is so foundational, so woven into the architecture of modern civilization, that almost nobody has ever stopped to question it. It's the kind of thing you simply know. The way you know the sun rises in the east or water flows downhill. Clocks, calendars, time zones. The entire scaffolding of organized human life was constructed around this one idea that Earth is a reliable, steady, predictable timekeeper. For centuries, it worked. The planet spun. We built on top of that spin. Cities synchronized, networks connected. The global economy found its rhythm. And then, starting around 2020, the ground shifted. Quietly, invisibly, but unmistakably. The International Earth Rotation and Reference System Service, IERS, doesn't make headlines often. It's a small, technical organization. Its job is precise and unglamorous: monitor the exact rotational speed of Earth using a global network of radio telescopes, laser stations, and satellite data. Then publish the results. Most years, nobody outside of specialized scientific circles pays much attention. Beginning in 2020, they started paying very close attention. That year, Earth began breaking its own speed records. July 29th, 2022, shortest day of 2022, beaten only weeks later. The years 2020 through 2022 produced the 28 shortest days ever recorded in the history of atomic timekeeping. Records fell. Then, new records fell on top of those records. The trend was not a blip. It wasn't seasonal noise. Scientists at IERS flagged it as a genuine, sustained, statistically significant acceleration. The planet was spinning faster, and nobody fully understood why. To understand how strange this is, imagine a spinning top. When you launch it, it spins fast. Over time, friction and air resistance slow it down. Eventually, it wobbles, tilts, and falls. That's the natural trajectory of any rotating object. Losing energy, it slows down. It doesn't spontaneously speed back up. For 4.5 billion years, Earth has been following exactly that script. When the Moon first formed from a catastrophic collision early in our solar system's history, a day on Earth lasted only 6 hours. Since then, the gravitational tug-of-war between Earth and the Moon has steadily bled rotational energy away from our planet. The moon's tidal forces act like a giant, invisible brake pad pressed against Earth's spin. Day by day, millennium by millennium, the planet has been slowing down by roughly 1.4 milliseconds per century, 4.5 billion years of deceleration, a trajectory so consistent, so mathematically reliable, that scientists used it to calculate what days looked like hundreds of millions of years ago. And then, in the span of just a few years, that 4.5 billion year trend reversed direction. Not slowed, not paused, reversed. That's not a scientific anomaly. That's a plot twist on a geological scale. Do you know that the day you were born was longer than today? Not by much, not enough to feel, but measurably, verifiably, documentably longer. Every person alive right now, every single one, has lived their entire life on a planet that is imperceptibly, but relentlessly, speeding up its spin. The world you woke up in this morning rotates slightly faster than the world you were born into. That's not a metaphor. It's a measurement. Here's the good news technically. You're aging slightly slower than you would have on the Earth of 100 years ago. Fewer milliseconds per day add up, in the most absurdly trivial way, to a marginally shorter biological lifetime measured in absolute time. Congratulations! The bad news is that everything else about this situation is profoundly, structurally, and practically not fine. Because a faster spinning Earth doesn't just mean shorter days in the abstract. It means the most precise timekeeping systems ever built by human civilization systems that entire global networks depend on are now chasing a planet that refuses to stay on schedule. It means the atomic clocks in server rooms across the world, the ones that keep the internet synchronized down to the nanosecond, are measuring a reality that is slowly, inevitably diverging from the reality Earth is actually living in. 2 clocks, 1 planet, and they're no longer telling the same time. But if the day is getting shorter, what happens to the most accurate clocks on the planet? The atomic ones, when the Earth they're supposed to track simply refuses to cooperate. The answer is currently keeping internet engineers awake at night. Right now, there are 2 different kinds of second running simultaneously on this planet, and they are drifting further apart with every passing year. This isn't a philosophical debate about the nature of time. It's a live, unresolved, technically terrifying crisis sitting at the foundation of every networked system humanity has ever built. To understand what's breaking, you first need to understand what was built. In 1972, the world's timekeeping authorities agreed on a solution to a problem most people didn't know existed. They created 2 parallel time systems and designed them to stay synchronized. The first is International Atomic Time, known by its French abbreviation TAI. It's measured by an ensemble of over 400 atomic clocks distributed across more than 50 laboratories worldwide, ticking away based on the resonance frequency of cesium-133 atoms, a physical constant so stable it doesn't drift by even 1 second over 300 million years. TAI doesn't care about Earth. It doesn't care about seasons, tides, or the planet's rotation. It just counts. Perfectly. Forever. The second system is Coordinated Universal Time, or UTC. This is the time your phone displays, the time stamped on your emails, the time zone offsets your computer calculates when scheduling a meeting across continents. UTC is the global standard, but unlike TAI, UTC is tethered to something messy and biological, the actual rotation of Earth. Those 2 systems were designed to stay within 0.9 seconds of each other. When Earth's rotation drifted slow enough that the gap approached 1 full second, timekeepers would insert a leap second, a deliberate, announced pause, in which UTC clocks held at a specific moment for 1 extra second while the atomic count continued. letting Earth catch up. It was an elegant, if slightly awkward, maintenance procedure. Think of it as manually syncing a wristwatch that runs just a little slow. The problem is that the watch isn't running slow anymore. Atomic clocks measure absolute physical time with inhuman precision. Earth, meanwhile, does not consult the schedule. It spins based on the combined influence of its molten core, its oceans, its atmosphere, the gravitational pull of the moon, the redistribution of mass from melting ice sheets, and forces that scientists are still working to fully map. For most of recorded history, those forces collectively acted as a brake. Earth was slowing. UTC needed leap seconds added positive ones, meaning clocks paused to let the planet catch up. Since 2020, that equation has inverted. Picture two people, each carrying a timepiece. One carries a Swiss atomic clock, the most precise instrument ever constructed, ticking with crystalline regularity derived from quantum physics. The other carries something stranger, a clock driven by the literal heartbeat of a spinning planet, calibrated to the wobble of molten iron and the weight of glaciers. For most of history, the planetary clock ran slightly slow. The two keepers would occasionally pause, let the planet clock catch up, and continue walking in step. Now the planet clock is running fast, and the two keepers are walking in opposite directions. Since 1972, humanity has inserted 27 positive leap seconds into UTC 27 moments where the world's clocks collectively paused for one extra tick to accommodate Earth's gradual slowdown. The most recent was added on December 31st, 2016. Since then, not a single one has been needed. The planet began accelerating. The gap between TAI and UTC stopped widening in the familiar direction and began developing pressure in the opposite one. For the first time in the history of atomic timekeeping, scientists are now confronting the possibility that instead of adding a second, they may need to subtract one. If you have two clocks that are off by 1 second, does it actually matter? In your kitchen? No. In your schedule? Barely. But step outside the comfortable scale of daily life, and 1 second becomes a chasm that can swallow entire systems whole. Modern financial markets operate in microseconds, millionths of a second. High-frequency trading algorithms execute thousands of transactions in the time it takes a human eye to blink. A 1 millisecond that's 1,000th of a second discrepancy in timestamps between servers can mean the difference between a legitimate trade and a regulatory violation, or trigger cascading automated sell-offs that produce what's known as a flash crash. GPS satellites calculate your position by measuring how long it takes a signal to travel from orbit to your device. The math runs on nanoseconds, billionths of a second. The global internet is synchronized through a protocol called NTP, Network Time Protocol, which distributes precise time from a hierarchy of atomic clock sources to every server, router, and data center on Earth. These systems don't just prefer accuracy, they require it the way a bridge requires its bolts. Remove the bolts, the bridge doesn't get slightly less stable, it falls. 1 second, in the context of the infrastructure running beneath modern civilization, is not a rounding error. It is a structural failure waiting for a date. Humanity spent centuries fighting over how to unify time zones. It took international treaties, diplomatic negotiations, and decades of infrastructure overhaul just to agree that everyone's clocks should show the same hour when they cross the same longitude. That achievement, global temporal synchronization, is one of the quiet, invisible foundations of the modern world. Air traffic control, international banking, military coordination, internet routing. All of it depends on the premise that every node in the network agrees on what time it is. Earth just decided, unilaterally, and without consulting any treaty, to change the terms of that agreement. And to patch the discrepancy, Scientists are now seriously considering a fix that has never been attempted in the entire history of global timekeeping, a fix so unprecedented that the software governing the world's networks was never written to handle it. A fix that could take the internet down with it. For the first time in history, the International Earth Rotation and Reference System Service is in serious, active discussion about subtracting 1 second from the global calendar, not adding one, removing one. A negative leap. Second, an event that has never happened. A scenario that sits entirely outside the operational assumptions of virtually every piece of software ever written to manage networked time. To understand why that's alarming, start with what positive leap seconds, the normal kind, have already done. On June 30th, 2012, a positive leap second was inserted into UTC at midnight. Clocks around the world were held at 23 hours, 59 minutes, and 59 seconds for 1 extra second before rolling over to the next day. It was a routine procedure, announced months in advance, carried out with the quiet confidence of something that had been done successfully before. Within hours, Reddit went down, Mozilla crashed, Linux-based systems across the internet began throwing errors, Qantas Airlines check-in systems failed, grounding flights and stranding passengers. The problem, countless servers, encountering the duplicate second, locked into processing loops they had no instruction to exit. The same second appeared twice. The software had no framework for that reality, so it seized. In 2017, Cloudflare, a company whose infrastructure handles traffic for millions of websites globally, experienced a similar failure during another positive leap second insertion. Its servers began calculating negative time intervals, interpreting the repeated second as time flowing backward, and started refusing connections. For a company built on the premise of keeping the internet running, watching it glitch over a single extra second was, by their own engineers' account, deeply uncomfortable. Both of those incidents involved adding a second the scenario. The entire system was at least nominally designed to anticipate, however imperfectly. A negative leap second is something else entirely. Imagine the clock on your wall. It reads 11:59 and 58 seconds. 1 second passes. Instead of advancing to 11:59 and 59, the clock jumps backward to 11:59 and 57. Your brain would catch it, flag it as wrong, and override it with common sense. You'd check your phone and move on. A server cannot do that. A server processes timestamps sequentially. Time, in the logical architecture of software, only moves forward. The entire edifice of database management, transaction logging, security certificates, and network synchronization is constructed on the axiom that the next timestamp will always be larger than the last one. When a negative leap second hits, that axiom breaks. Systems that compare the current time to the previous time and act based on the difference encounter a negative interval, a number that their logic says is impossible. Some will crash, some will stall, some will begin making decisions based on corrupted timing data without flagging an error at all. The last scenario is the most dangerous because the system appears to be functioning normally while producing subtly wrong outputs. The tech industry is not unaware of this problem. In 2022, Meta, the company behind Facebook, Instagram, and WhatsApp, published a formal position paper calling for the complete abolition of the leap second system. Their engineers described it as a significant source of operational risk that had already caused documented incidents and would cause worse ones in the future. Google, for its part, developed a workaround called the leap smear, instead of inserting or removing a single abrupt second. Their servers distribute the adjustment across the preceding 12 hours, shaving or adding fractions of milliseconds continuously until the offset is absorbed. It's a clever engineering solution to a problem that, by rights, shouldn't exist. But Google's smear doesn't solve the underlying reality. It just manages the symptom at one company's infrastructure. The broader ecosystem, the thousands of banks, hospitals, power utilities, telecommunications providers, and government systems running on a vast patchwork of software built across decades, has no universal smear. Each system handles time in its own way, with its own assumptions, and those assumptions do not include the second hand going backward. Does 1 second sound too small to cause a global financial crisis? Walk through the arithmetic. High-frequency trading systems in markets like the New York Stock Exchange execute transactions on timescales of microseconds. They rely on synchronized timestamps to establish the legal sequence of trades: who bought first, who sold first, what price was legitimate, and what was front-running. A negative leap second, depending on implementation, can create a window where two events appear to have the same timestamp, or where sequence inverts. Automated systems detecting anomalies will trigger circuit breakers. Circuit breakers trigger cascading sell orders. Cascading sell orders produce the exact profile of a flash crash. The 2010 flash crash, in which the Dow Jones Industrial Average fell nearly 1,000 points in minutes before partially recovering, was triggered by a single, large algorithmic order interacting unexpectedly with automated trading systems. A global timestamp anomaly would hit every market simultaneously. Then there are hospital ICU systems, where medication pumps and ventilators log every intervention with precise timestamps to ensure patients receive the correct doses at the correct intervals. Power grids, where synchronized timing across transmission nodes keeps alternating current flowing. At 60 Hz, a deviation of a fraction of a second in synchronization can cascade into regional blackouts. The Northeast blackout of 2003, which cut power to 55 million people across the northeastern United States and Canada, began with a software bug in a single alarm system that prevented operators from seeing a cascading failure in real time. 1 second, one backward tick, and every one of those systems has to decide, in real time, what to do with a timestamp that their entire architecture told them was impossible. Humanity spent years terrified of Y2K, the fear that software written with two-digit year fields would catastrophically misread the year 2000 as the year 1900. Governments spent an estimated $300 billion globally preparing for it. The actual damage was minimal, largely because the problem was visible, nameable, and fixable in advance. A negative leap second is narrower, faster, and far less predictable in its downstream effects. The window is 1 second. The failure modes are distributed across millions of systems. And unlike Y2K, there is no universally agreed fix, just a planet spinning slightly too fast, and an industry hoping the adjustment never actually comes. The internet is only the surface layer of this problem. 20,000 kilometers above your head, there are hundreds of satellites in silent, precise orbit, and they are navigating the same crisis. Right now, they are guiding your pilot toward the runway. A GPS timing error of just 1 microsecond, 1/1,000,000th of a second, translates into a positional error of 300 meters. And when Earth rotates faster than the satellite's calculations expect, the planet's surface physically runs ahead of where the orbital geometry says it should be. That sentence deserves a moment of stillness before moving forward. 300 meters, from a single microsecond, in a world where commercial aircraft execute precision instrument approaches in near-zero visibility, where autonomous ships navigate crowded ports without a human hand on the wheel, where self-driving vehicles make lane decisions at highway speeds, 300 meters is not a margin of error. It's the distance between a runway threshold and the edge of a forest. To understand the mechanism, start with how GPS actually works, because most people carry a fundamental misunderstanding of it. GPS does not measure distance directly. It measures time. A GPS receiver, listens to signals from multiple satellites simultaneously, each signal stamped with the exact moment it was transmitted from orbit. The receiver calculates how long each signal took to arrive. Since those signals travel at the speed of light approximately 299,792,458 meters per second, even a few nanoseconds of travel time difference translates into a precise triangulated position on Earth's surface. The whole system is at its core an extraordinarily sophisticated clock network dressed up as a map. This means GPS is only as accurate as its timing, and its timing assumes something critical, that it knows exactly where Earth's surface is at any given moment, relative to the orbital positions of the satellites above it. That knowledge is encoded in a reference framework called WGS-84, the World Geodetic System established in 1984. It's a mathematical model of Earth's shape, size, and rotational behavior, and it serves as the common coordinate language between every satellite in the GPS constellation and every receiver on the ground. When a pilot's navigation display shows the aircraft is 3 miles from the runway threshold at an altitude of 1,500 feet, that number is an output of WGS-84's assumptions about where Earth's surface is and how fast it's moving. When Earth accelerates beyond those assumptions, WGS-84's rotational parameters begin to drift from physical reality. The surface moves faster than the model expects. Coordinates shift. The gap is small, measured in fractions of meters at current acceleration rates, but it compounds over time. And it is not uniform. It varies by latitude, by the geometry of the satellite constellation overhead at any given moment, and by the specific application relying on the data. For most consumer uses, navigating to a restaurant, tracking a package, the error is invisible. For precision-critical systems operating at the boundary of their safety tolerances, it is anything but. The Federal Aviation Administration and the International Civil Aviation Organization both monitor GPS integrity continuously, and both maintain what are called NOTAM systems, notices to air missions that flag GPS anomalies to flight crews in real time. These systems exist precisely because GPS errors happen, and because the aviation community learned through painful experience that a navigation system trusted absolutely is a navigation system that can kill you when it fails quietly. What's changed in recent years is not the existence of GPS anomalies, but the nature of their source: satellite hardware failures, solar interference, intentional jamming. These have known signatures and known responses. A planet spinning faster than its own coordinate system expects is a different category of problem. It's systemic, it's continuous, and it affects every receiver on the surface simultaneously. The last time you boarded a commercial flight, your pilot was almost certainly using GPS-augmented navigation for at least part of the approach. Modern instrument landing systems increasingly integrate GPS precision approach data, which guides aircraft to within meters of the runway centerline in conditions where visual reference is impossible. The FAA's Wide Area Augmentation System, known as WAAS, provides GPS accuracy down to approximately 3 meters horizontally and 4 meters vertically across the contiguous United States. That level of precision is what allows a 350-ton aircraft to find a strip of concrete in fog. It is predicated on the assumption that the mathematical model of Earth's rotation underpinning every GPS calculation is current and correct. And it's not just aircraft. The Port of Rotterdam, the world's largest seaport outside Asia, now operates partially autonomous container vessels that navigate using GPS positioning accurate to centimeters. Autonomous mining trucks in the Pilbara region of Australia carry hundreds of tons of ore across GPS-guided routes without drivers. Agricultural machinery across the American Midwest plants crops in rows guided by sub-centimeter GPS precision, maximizing yield per acre across millions of hectares. In 2022, the U.S. Department of Defense acknowledged that GPS-dependent precision munitions represent the overwhelming majority of guided weapons in the American arsenal. The entire operational architecture of modern warfare, modern logistics, modern agriculture, and modern transportation is threaded through the same timing infrastructure. We have come to trust GPS with a completeness that borders on the theological. People have driven into lakes because a navigation app told them to turn right. They've followed GPS routes onto closed mountain passes in winter. They've guided boats onto sandbars following outdated chart data relayed through navigation systems. In every case, the error wasn't malicious. It was the failure mode of absolute trust, the assumption that the technology is simply always correct. At least the lake is stationary. Earth is not. The planet is moving faster than the model that describes it. That gap is currently small enough that most systems compensate through continuous calibration and correction updates pushed to GPS satellites through ground control stations. But calibration is reactive. It corrects for errors that have already accumulated, not errors that are developing in real time. And as Earth's rotational acceleration continues, the frequency and magnitude of those corrections will need to increase to match it. Everything discussed so far the shorter days, the drifting clocks, the satellites losing their grip on where the ground actually is, these are symptoms, observable, measurable, consequential symptoms, but they are not the cause. The cause lies deeper than any of this, deeper than oceans, deeper than tectonic plates, deeper in the most literal sense of the word, than almost anything humans have ever attempted to study, approximately 5,000 kilometers beneath your feet. There is an ocean of liquid iron at 4,000 degrees Celsius churning directly beneath your feet right now, and it has just changed the direction of its flow in a way that scientists have never observed before. Not a metaphor, not geological shorthand, a literal ocean. Liquid metal. Superheated to temperatures that dwarf the surface of the sun's outer atmosphere, sloshing and surging in currents that span thousands of kilometers, moving at speeds measured in kilometers per year, slow by human standards, catastrophically fast by geological ones. This is Earth's outer core, and it is not behaving the way it used to. To place it physically, Earth is structured in layers, like a hard-boiled egg scaled to the size of a planet. The thin, brittle crust you walk on, oceanic and continental averages, roughly 35 kilometers thick under continents, far thinner under ocean floors. Beneath that lies the mantle, a layer of hot but solid silicate rock extending approximately 2,900 kilometers deep, capable of flowing on timescales of millions of years under immense pressure. Then the outer core begins. It is a shell of liquid iron and nickel 2,300 kilometers thick, surrounding an inner solid core at the planet's absolute center. The outer core exists in liquid form because despite being under extraordinary pressure, the temperature is too high for the metal to solidify. The result is a global ocean of electrically conductive metallic liquid, perpetually in motion. And that motion is what makes Earth habitable. As the liquid iron in the outer core convects hot material rising, cooler material sinking, the whole mass rotating with the planet while also churning internally, it generates electric currents. Those currents, moving through a conducting fluid in a rotating system, act as a dynamo. They produce Earth's magnetic field. That field extends far out into space, deflecting the constant stream of charged particles blasting outward from the sun, bending away cosmic radiation that would otherwise strip the atmosphere and sterilize the surface. Without the outer core's churning, that field weakens. Without the field, Earth becomes Mars, a desiccated, irradiated rock with a thin atmosphere and no meaningful protection for anything attempting to live on its surface. The convection currents in this liquid metal ocean do something else, too. They push. As those massive flows circulate, they exert torque rotational force on the solid mantle above them. The mantle transmits that force upward to the crust. The relationship between the outer core's circulation patterns and the rotation rate of Earth's surface is mechanical, like a system of gears. When the patterns in the core shift, the transmission of angular momentum upward through the mantle changes with it. The surface speeds up or slows down in response. This is the deep mechanical engine behind everything discussed so far. The shorter days, the accelerating rotation, the pressure building on every system built to assume that Earth's spin is constant. It all traces back, at least in part, to changes in the circulation of a liquid metal ocean 3,000 kilometers beneath the nearest bedrock. In 2023, research drawing on data from the European Space Agency's Swarm satellite constellation, 3 satellites specifically designed to measure Earth's magnetic field with extreme precision, documented anomalous changes in the flow patterns of the outer core. Swarm doesn't image the core directly. Nothing can. But magnetic field variations at the surface carry information about what's happening in the conducting fluid below. The way ripples on a lake's surface carry information about what's moving underneath. By mapping those magnetic variations with extraordinary spatial and temporal resolution, geophysicists can reconstruct the large-scale flow patterns in the outer core indirectly. What they found was that the patterns were shifting in ways that don't match prior behavior in the observational record. Think of it this way. When you stir water in a bathtub with your hand, the water pushes back against the walls of the tub. The force isn't enormous, but it's real, you can feel it. Now scale that up a 2,300 kilometer thick layer of liquid metal, heated to 4,000 degrees Celsius, rotating and convecting inside a spherical shell the size of a planet, changing its circulation patterns. The force it exerts on the mantle above is not trivial. It is, in fact, one of the primary mechanisms by which the rotation rate of Earth's surface changes over timescales of years to decades. Has it ever occurred to you that the thing protecting you from cosmic radiation is a boiling underground ocean of liquid iron? Probably not. It's not the kind of thing that comes up at dinner, but it should, because that ocean is not static and its behavior is not decoupled from the world above it. The same circulation changes that are contributing to Earth's acceleration are also contributing to the slow deterioration of the magnetic field, the shield that stands between life on this surface and the full intensity of the space environment. 2 consequences, 1 cause, operating simultaneously, and we are only now developing the observational tools sophisticated enough to watch it happen in real time. We spend enormous collective energy worrying about what's happening to the air above us, particulate matter, greenhouse gases, ozone depletion. These are real concerns with real consequences. But beneath the deepest mine shaft ever drilled, beneath the deepest borehole ever attempted, beneath the ocean floor and the mantle rock below it, a planetary-scale steel mill is making decisions about the fate of everything on the surface. And it is doing so in complete indifference to any of our concerns. The outer core is only part of the story, though at the absolute center of this planet, deeper than the outer core, deeper than any layer discussed so far, something stranger still is happening. A solid iron sphere the size of the moon just reversed the direction of its rotation. In 2023, a study published in Nature Geoscience confirmed something that geophysicists had suspected, but never been able to prove with sufficient evidence. Earth's inner core, a solid iron sphere roughly 2,440 kilometers in diameter, approximately the size of the moon, had slowed its rotation, come to a near halt relative to the surface, and was in the process of rotating in the opposite direction, not wobbling, not drifting slightly, reversing. To grasp what this means, you first need to understand what the inner core actually is, because it's one of the most physically improbable objects in existence. Deep inside the liquid iron ocean of the outer core described earlier, under pressures so extreme that they reach 3.6 million times the atmospheric pressure at sea level, iron that would otherwise be liquid is forced into a solid state despite temperatures exceeding 5,000 degrees Celsius hotter than the surface of the sun. The result is a ball of solid metal suspended freely inside the outer core's liquid, touching nothing solid, anchored by nothing mechanical, held in place only by the gravitational symmetry of the planet around it. And because it touches nothing solid, it can rotate independently of everything above it. The inner core floats inside the outer core, the way a hard-boiled yolk floats inside a liquid white, except the white is liquid metal at thousands of degrees, and the yolk is a moon-sized iron sphere spinning at its own pace, governed by the interplay of magnetic forces from the outer core's dynamo and the gravitational influences of the mantle above. Under normal circumstances, the inner core rotates slightly faster than the surface, a phenomenon called superrotation. For decades, this was the scientific consensus, inferred from subtle but consistent patterns in seismic wave data. The way we know anything about the inner core at all is itself extraordinary. No drill has ever come close to reaching it. No instrument will ever be physically lowered into it. What geophysicists have is seismic waves, the energy released by earthquakes, and, crucially, by underground nuclear weapons tests. When a massive earthquake or a nuclear detonation occurs, it sends seismic waves radiating outward in all directions, including straight down through the planet. Some of those waves pass entirely through the inner core and emerge on the other side. The precise timing and waveform of those transmitted signals carry information about the material they traveled through, its density, its temperature, its orientation, and its motion. Yang and Xiaodong Song at Peking University spent years building a dataset of seismic wave recordings from nuclear tests conducted by the United States and the Soviet Union beginning in the 1960s, combined with recordings from major earthquakes over the same period. By comparing how waves from the same geographic corridors changed over decades, arriving fractions of a second, faster or slower, their waveforms slightly altered, they reconstructed the rotational history of the inner core with a precision that had not previously been achievable. Their 2023 analysis concluded that sometime around 2010, the inner core's superrotation slowed to essentially zero, and since then has been rotating at a rate slightly behind the surface, meaning, relative to where you are standing, the inner core is drifting backward. The mechanism connecting this reversal to Earth's accelerating surface rotation is angular momentum conservation, one of the most ironclad principles in physics. In a closed system, total rotational momentum cannot be created or destroyed. It can only be transferred between components. When a figure skater pulls their arms inward, they spin faster because their rotational momentum is being concentrated into a smaller radius. When they extend their arms outward, they slow down because that momentum spreads back out. The inner core, the outer core, the mantle, and the crust form a coupled system in which angular momentum flows between layers continuously. When the inner core slows down, that rotational momentum doesn't vanish. It transfers outward through the coupling between the inner core and the outer core's magnetic field, and from there upward through the mantle and into the crust. The surface speeds up to compensate. The relationship isn't perfectly direct or instantaneous. There are time lags and filtering effects as the transfer propagates through each layer. But the directional consequence is clear. A decelerating inner core means an accelerating surface. Think of it as two gears in a planetary transmission. When the inner gear loses speed, the outer gear gains it. The system conserves its total energy. It doesn't ask permission. It doesn't post a warning. it just redistributes. The oscillation itself appears to operate on a cycle of approximately 70 years, based on the seismic record extending back through the 20th century. The inner core speeds up, then slows, then reverses again, a slow planetary breathing that transfers momentum back and forth between the deep interior and the surface. If the 70-year estimate is correct, the last major reversal would have occurred around the 1970s, and the one before that around 1900. We are, by this reckoning, at or near the peak of the current reversal phase, which means the transfer of angular momentum to the surface that's been driving the acceleration of Earth's rotation may still have years to run before it begins to taper. Does it strike you, right now, that the planet you are standing on is essentially a clockwork machine, one that has been quietly winding and unwinding itself for billions of years, adjusting its own rotation through the interplay of its internal layers, completely independent of anything happening on the surface? Every city ever built, every civilization ever assembled, every calendar, every clock, every GPS satellite ever launched, all of it sitting on the outermost shell of a self-regulating mechanical system that operates on timescales of decades and centuries and eons, and that has never once paused its adjustments to accommodate the infrastructure sitting on top of it. Humanity is enormously proud of having reached the moon. The Apollo missions remain one of the most extraordinary achievements in our species' history. 250,000 miles of empty space, crossed by human beings in a vehicle not much larger than a minivan. But there is an object the size of the moon sitting directly beneath your feet, and everything we know about it was inferred by listening to the echoes of nuclear explosions bouncing through the planet's center. We have touched the moon. The inner core remains as alien to us as a distant star. The inside is pushing outward. Angular momentum flowing from center to surface, driving the acceleration that's shortening every day and pressuring every timekeeping system on the planet. But simultaneously, something above is pulling in the opposite direction, redistributing the planet's own mass in ways that nobody predicted, and doing it through a mechanism so mundane, so ordinary, so thoroughly human in its origin, that the scale of its consequences seems almost impossible to believe. NASA has confirmed that Earth's rotational axis has shifted by approximately 4 meters since 1990, and the primary cause is not earthquakes, not volcanic eruptions, not some extraordinary geological event. It's groundwater pumping. Let that settle for a moment. 4 meters. The pole around which this entire planet rotates has physically migrated 4 meters from where it was 35 years ago, and we did it by pulling water out of the ground. Earth's rotational axis is not a rigid steel pin. It's a dynamic equilibrium, a balance point determined by how mass is distributed across the entire planet. The axis can and does move naturally, oscillating within a range of a few meters over periods of years and decades, driven by the slow redistribution of mass through geological processes, atmospheric changes, and ocean circulation. This natural wandering of the poles has been observed and measured for well over a century. What's changed is the scale, the speed, and the cause. Greenland's ice sheet is losing approximately 280 billion tons of ice per year. Antarctica is losing approximately 150 billion tons per year. These numbers are not projections or model outputs. They come from direct satellite measurements, principally from the GRACE and GRACE-FO satellite missions, which map Earth's gravitational field with extraordinary precision and track changes in mass distribution over time. As that ice melts, the water flows into the global ocean, redistributing an enormous amount of mass away from the poles and toward lower latitudes. To see why this shifts the rotational axis, imagine a ballet dancer spinning on one foot with heavy weights strapped to both wrists, held close to the body. The weights concentrated near the spin axis keep the rotation stable and centered. Now imagine those weights are released and slide outward, away from the center, redistributing toward the dancer's extended arms and away from the axis of spin. The center of gravity shifts, the axis tilts. The entire rotational geometry of the system responds to where the mass is. Earth operates on exactly this principle, just at a scale that staggers the imagination. Billions of tons of water, previously locked as ice near the poles close to the rotational axis, contributing relatively little to the planet's rotational inertia, are migrating into the ocean, spreading across the globe, concentrating at lower latitudes. The redistribution of that mass shifts the axis in response. Physics doesn't offer an exemption, but ice melt is only part of the story. In 2023, a study published in Geophysical Research Letters by Seo, On, Cho, and colleagues, using NASA data, added a finding that genuinely surprised the scientific community. Between 1993 and 2010, human extraction of groundwater water pumped from underground aquifers for agriculture, industry, and municipal supply totaled approximately 2,000 to 150 billion tons. That water was drawn from underground reservoirs distributed across the planet, transported to the surface, used, and eventually released into rivers and oceans, where it spread according to drainage patterns. This massive, human-driven redistribution of mass was sufficient, on its own, to shift Earth's rotational axis by approximately 80 centimeters toward the east, a contribution comparable in magnitude to the effects of ice melt. Did you know that every time the collective weight of human civilization draws water from underground billions of people, across decades, pulling aquifers down by meters, you are together, tilting the axis of the planet, not dramatically, not visibly on any human scale, but measurably, permanently, on the time scale of centuries. The water that was underground is now in the ocean. It isn't going back into the aquifer. The mass has moved, and the axis has followed it. The implications extend beyond the abstract. A shifted rotational axis means the geographic poles, the points where the axis intersects the surface, move. Polar drift, as it's technically called, has been happening for as long as Earth has existed, but the current rate of drift has accelerated significantly since the middle of the 20th century, driven by both the glacial processes and the human water extraction documented above. The North Pole is currently drifting toward Greenland and the British Isles at a rate that has roughly tripled compared to its average velocity in the early 20th century. Over geological timescales, polar drift influences which parts of Earth receive how much solar radiation across the seasons, a factor in long-term climate evolution. On shorter timescales, it creates subtle but measurable changes in regional climate patterns that accumulate over decades. And on the technical level, it feeds directly back into the GPS problem described earlier. Because the coordinate systems used by satellite navigation are anchored to the position of Earth's rotational axis. And when that axis moves, the coordinates shift with it. Superheroes in comic books worry about villains with machines designed to tilt Earth's axis. The scenario is always presented as requiring godlike technology, a megalomaniacal plan, and a dramatic confrontation to prevent. It turns out that 8 billion people irrigating crops and flushing toilets have been accomplishing the same thing more efficiently and with considerably less drama for decades, without anyone planning it or even noticing until satellites got precise enough to measure it. The axis has shifted, but the consequences don't stop there. It's beginning to disrupt one of the most delicate rhythms on the planet, a wobble that, if lost, leaves the entire global climate system without an anchor. Earth has a natural wobble called the Chandler Oscillation, and between 2017 and 2020, it nearly vanished entirely. No one has a complete explanation for why. This is not a minor footnote in geophysical literature. The Chandler wobble has been one of the most reliably observed motions in Earth science since Seth Carlo Chandler first described it in 1891. It is, in a very real sense, the planet's own heartbeat, a slow, rhythmic sway of the rotational axis that has persisted with remarkable consistency for as long as it has been measured. And then, for roughly 3 years, spanning the late 20-teens, its amplitude dropped to near zero. The heartbeat didn't race, it didn't arrhythmia, it simply became almost inaudible. To understand what was lost, you need to understand what the Chandler wobble actually is. Earth's rotational axis, the invisible line running from pole to pole around which the planet spins, does not stay fixed in space. It moves. Some of this movement is predictable and well understood. The slow, 26,000-year precession cycle caused by the gravitational tug of the Moon and Sun. The shorter nutation cycles driven by lunar orbital geometry. But superimposed on all of these is a shorter, quirkier motion. Discovered by Chandler, the geographic poles trace a rough circle of approximately 9 meters in diameter at the surface, completing one loop in roughly 14 months. This is the Chandler wobble. It arises because Earth is not a perfect sphere. The planet bulges at the equator. The equatorial radius is about 21 kilometers larger than the polar radius, and this flattening means that the axis of maximum rotational inertia and the actual spin axis don't perfectly coincide. In a rigid body, this misalignment would produce a stable oscillation. In a real, deformable planet with oceans and an atmosphere, the wobble interacts with the fluid layers, drawing energy from and depositing energy into the ocean and atmosphere in ways that are still not fully modeled. This 14-month Chandler oscillation combines with a separate 12-month oscillation driven by the annual redistribution of mass from atmospheric pressure patterns and seasonal water cycles. The two together produce a complex figure 8-like path traced by the geographic poles across the surface, a motion that geodesists and astronomers have tracked with increasing precision since the late 19th century. The path wanders, the amplitude varies, but the fundamental rhythm has always persisted. Because the geographic poles are constantly moving, any system that requires precise knowledge of where the poles are at any given moment must account for that movement. GPS satellite constellations depend on it. Astronomical observatories use it to correct telescope pointing. The precise timing of signals between ground stations and space assets depends on knowing, to within centimeters, where each station actually is on a rotating, wobbling Earth. The International Earth Rotation and Reference System Service publishes what are called Earth orientation parameters, daily updates to the exact position of the poles and the precise rotational rate of the planet. And these parameters are distributed to every major navigation system, space agency, and geodetic network on Earth as a matter of operational necessity. When the Chandler wobble's amplitude began declining sharply around 2017, reaching its lowest recorded level in the 2017 to 2020 period, the scientific community noticed. Research teams, including those associated with the Pulkovo Astronomical Observatory in Russia, and analysts at NASA's Jet Propulsion Laboratory, documented the suppression in the observational record. What they could not definitively answer was why it happened. The leading hypothesis involves changes in the distribution of ocean mass specifically. The combination of rising sea surface temperatures, altering the density and pressure fields of the upper ocean, and shifts in deep ocean circulation patterns redistributing water mass across the globe. The Chandler wobble requires a continuous source of energy to sustain itself against the damping forces of the planet's deformable layers. That energy comes primarily from the ocean bottom pressure variations that excite and maintain the oscillation. When those pressure patterns change, as they do when ocean circulation shifts and thermal expansion redistributes mass, the energy input to the wobble can weaken. If it weakens enough, the amplitude drops. If the source of excitation changes character significantly, The wobble can be suppressed for years before reasserting itself in a modified form. Think of a gyroscope, a spinning top designed to maintain its orientation through rotational inertia. When the weight distribution around the gyroscope's axis is uniform and stable, it precesses smoothly and predictably. Disturb that distribution unevenly, add mass to one side, remove it from another, and the precession becomes irregular. Disturb it severely enough, and the gyroscope's stability begins to fail, the oscillation becoming erratic or dying out entirely before the system finds a new equilibrium. Earth's wobble behaves analogously. The mass distribution that drives it the particular arrangement of ocean water, ice, atmosphere, and mantle material that continuously excites the Chandler oscillation, has been disrupted by the same forces rearranging everything else: warming oceans, melting ice, shifting circulation patterns. The wobble didn't disappear because something catastrophic happened. It faded because the energy source sustaining it quietly changed. Your planet has its own heartbeat. Between 2017 and 2020, it skipped for 3 straight years. Are you concerned? A cardiologist presented with a patient whose heart rhythm disappeared for 3 years and then quietly returned would not call that a resolved incident. They would call it an unexplained event requiring very serious ongoing monitoring, because unexplained arrhythmias that come and go without clear cause are, in the language of medicine, a warning that the system is under stress it hasn't yet declared. Geophysicists use different vocabulary but reach similar conclusions. The difference, of course, is that a patient in distress can tell you what they feel. They can describe the tightness in the chest, the skipped beat, the moment it happened. Earth communicates exclusively through instruments, seismometers, satellites, magnetometers, tide gauges, and only to the extent that someone thought to build the instrument and position it correctly. Much of what Earth has been trying to say for the past decade, we are only now learning to read. The inner core is shifting its rotation. The outer core is changing its flow. The axis has migrated. The wobble went quiet. Each of these is a signal from a different layer of the same planetary system, all arriving at roughly the same time. And while all of this has been unfolding deep inside and across the surface of the planet, the invisible shield protecting every living thing from the violence of space has been quietly coming apart at the seams. Earth's magnetic field has weakened by 9% since 1840, and there is a region above the South Atlantic Ocean where the field has grown so faint that satellites passing through it malfunction with enough regularity that space agencies have given it a name and built mission protocols around it. 9% in roughly 180 years sounds like a slow, manageable decline. It isn't. In geological terms, 180 years is less than a breath. The rate of weakening observed since systematic measurement began is, by the standards of the paleomagnetic record, extraordinarily rapid. And it is not uniform across the planet. It is concentrated, directional, and accelerating in specific regions in ways that have begun to draw genuine alarm from researchers who are not, by professional temperament, given to alarm. To understand what's at stake, start with what the magnetic field actually does. The field extends from Earth's interior out into space, forming an asymmetric bubble called the magnetosphere that deflects the solar wind, the continuous stream of charged particles ejected from the sun at speeds between 300 and 800 kilometers per second and bends away cosmic rays, the high-energy particles originating from supernovae and other violent events across the galaxy. Without this deflection, those particles would reach the surface unimpeded. They would ionize atmospheric molecules, accelerate the chemical destruction of the ozone layer, and deliver radiation doses to surface life that current biology is not equipped to tolerate at sustained levels. The field is not a convenience. It is the prerequisite for complex life on this planet, as fundamental as the presence of liquid water or oxygen. The South Atlantic anomaly is a region centered roughly over the South Atlantic Ocean and extending over parts of South America and Southern Africa, where the magnetic field is dramatically weaker than average and sits anomalously close to Earth's surface. Under normal conditions, the inner boundary of the radiation belts, the regions of trapped charged particles that the magnetic field holds at bay, sits comfortably far above the atmosphere. Over the South Atlantic anomaly, that boundary dips much lower. Satellites crossing through it are exposed to particle fluxes intense enough to cause single event upsets in electronic systems, bit flips, memory corruption, processor errors triggered by individual energetic particles passing through semiconductor components. The International Space Station crosses the South Atlantic anomaly on many of its orbits and has documented protocols for the passage. Certain sensitive instruments are powered down. Crew exposure is monitored, and operations requiring high computational reliability are scheduled outside the anomaly window. The Hubble Space Telescope, operating in a similar orbital altitude, has logged a disproportionate share of its technical anomalies while transiting this region. These are not theoretical risks. They are operational realities that space agencies have been managing for decades. What changed is the anomaly's behavior. Data from the European Space Agency's Swarm satellite constellation, published in 2020, showed that the South Atlantic anomaly is not only persisting, but expanding, and that it appears to be developing a second center of minimum field intensity to its southwest, suggesting the anomaly may be splitting into two distinct regions of weakness, rather than remaining as a single feature. The rate of westward drift of the anomaly's center has also accelerated. The structure is not static, it is evolving, and the direction of that evolution is toward greater spatial extent and deeper field depression. The connection to what's happening inside Earth is direct. The magnetic field is generated by the circulation of conducting fluid in the outer core, the same liquid iron ocean discussed earlier, whose flow patterns have been shifting in ways the swarm data has been documenting. When those flow patterns change, the dynamo they drive changes with it. Field strength varies regionally. Anomalous zones grow or shrink. The overall dipole, the dominant north-south orientation of the field, can weaken or strengthen depending on how the core's convective cells are organized at any given time. The magnetic North Pole, the point toward which compass needles point, is not fixed. It wanders. Throughout most of the 20th century, it drifted at a relatively modest pace, approximately 15 kilometers per year, moving generally northward from its position in northern Canada. Then, in the 1990s, it began accelerating. By the early 2000s, the drift rate had increased substantially. By the late 20-teens, it had reached over 50 kilometers per year, more than 3 times its earlier velocity, moving so rapidly that the World Magnetic Model, the standard reference used by navigation systems worldwide, had to be updated ahead of its normal 5-year revision schedule in 2019 because the pole had moved far enough to introduce meaningful errors into compass-based navigation. The magnetic North Pole has now left Canadian territory entirely and is crossing the Arctic Ocean toward Siberia. What would happen if the magnetic shield collapsed entirely, even temporarily? The paleomagnetic record shows that during geomagnetic reversals, when the North and South poles exchange positions, the field doesn't simply flip instantaneously. It weakens, becomes chaotic, fragmenting into multiple weaker poles scattered across the planet, and may drop to as little as 10% of its current strength during the transitional period. That period can last anywhere from 1,000 to 10,000 years. During that time, the reduced field means elevated ultraviolet radiation reaching the surface, disruption to the chemistry of the upper atmosphere, and increased cosmic ray flux. We apply SPF 50 sunscreen to protect our skin from a fraction of 1% of the solar radiation that reaches the surface. The magnetic field is, in the most literal sense, Earth's SPF 10 billion. the factor by which it reduces our exposure to the full ferocity of the space environment. Right now, that SPF rating has dropped to roughly SPF 9 billion and falling, and the zone where it's weakest is directly over one of the most populated regions of the Southern Hemisphere. This is not the first time this has happened. In Earth's long geological history, the field has weakened, fragmented, and reversed many times. And what the rock record shows about what followed those episodes, what actually happened on the surface during those transitions, is precisely why the current trajectory is not being discussed calmly behind closed doors. It's being discussed urgently. Ancient rocks and 400-million-year-old fossil coral show that a day on Earth was once only 22 hours long, and every major magnetic pole reversal in Earth's history has coincided with periods of mass extinction. These are not interpretations. They are readings. The planet has been keeping its own records for billions of years, inscribed in stone and skeleton and sediment, and those records are now telling a story that scientists are reading with increasing unease. The discipline is called magnetostratigraphy, and its foundation is elegantly simple. When volcanic lava erupts and cools, the magnetic minerals within it, primarily magnetite, align themselves with the ambient magnetic field at the moment of solidification. Once the rock hardens, that alignment is locked in permanently. Like a compass needle frozen in place at a specific moment in time, layer volcanic rock sequences from different geological periods, and you have a physical archive of Earth's magnetic field stretching back hundreds of millions of years. Each layer is a timestamp. Each magnetic orientation is a data point. Together, they form a record of remarkable completeness, a planetary black box that doesn't burn in crashes, doesn't corrode, and doesn't lie. Reading it requires patience and precision, but the information it contains is unambiguous. Earth's magnetic field has reversed its polarity many times throughout geological history. What was magnetic north becomes magnetic south. The field weakens, fragments into chaotic multipolar configurations, and over timescales measured in hundreds to thousands of years, gradually reorganizes into a new stable dipole pointing in the opposite direction. This process has occurred approximately 183 times in the past 83 million years alone, an average of roughly one reversal every 450,000 years, though the intervals are highly irregular, ranging from tens of thousands to tens of millions of years between events. The most recent full reversal is called the Brunhes-Matuyama boundary, and it occurred approximately 780,000 years ago. Since then, Earth has been in the current Brunhes normal polarity epoch, the longest stable period of the same polarity in the past 80 million years. We are, by historical standards, overdue. But there is a more recent event in the record that carries even more direct relevance to the present, and it is far more disturbing than the Brunhes-Matuyama reversal. Approximately 42,000 years ago, Earth experienced what is now called the Lachant excursion, a brief but dramatic episode in which the magnetic field weakened to roughly 6% of its current strength, and the poles temporarily shifted to low latitudes before the field partially recovered and stabilized. It was not a full reversal, but the field during this period was so weak and so disorganized that the magnetosphere essentially ceased to function as a coherent shield. The cosmic ray flux reaching the surface increased dramatically. The chemistry of the upper atmosphere was radically altered, affecting ultraviolet radiation levels and the concentration of radioactive carbon-14 in the atmosphere. This event coincided within the resolution of the geological and archaeological record, with the disappearance of Neanderthals from the fossil record and with a wave of megafaunal extinctions across multiple continents. A 2021 study published in Science by Alan Cooper and colleagues used the Lachant excursion as a framework for understanding an extraordinary coincidence of environmental catastrophes. massive wildfires documented in the sediment record, radical vegetation shifts, climate instability, and the abrupt end of the Neanderthal lineage that had persisted in Europe and Western Asia for hundreds of thousands of years. The causal chain proposed is not that the magnetic field reversal directly killed individual organisms. It's that a sustained period of weakened shielding altered the radiation environment, disrupted atmospheric chemistry, amplified climate instability, and compressed the ecological margin available to species that were already under stress. The Neanderthals didn't disappear because cosmic rays were raining down. They disappeared because the world they were adapted to stopped being stable enough to support them. And that destabilization was at least partly driven by the same magnetic field deterioration we are measuring today at accelerating rates. The coral record adds a different dimension to the picture. Coral polyps secrete calcium carbonate skeletons and do so in a daily rhythm tied to tidal and solar cycles, producing growth bands analogous to tree rings, one per day. By counting the number of daily growth bands per annual band in fossil coral specimens, paleontologists can determine how many days were in a year at the time those corals were alive. The physics is straightforward. The number of days in a year is determined by dividing the year's duration by the length of a day. The year's duration has been essentially constant for billions of years. So, the number of daily bands per year directly reveals how long a day was. Fossil coral from the Devonian period, approximately 400 million years ago, consistently shows approximately 400 daily growth rings per year. 400 days per year, which means each day was approximately 21.8 hours long shorter than today's 24 hours by more than 2 hours. This is direct physical confirmation that Earth's rotation has been slowing over geological time, as angular momentum was steadily bled away by the gravitational braking of the Moon. Today, that deceleration has reversed, but the coral record shows unambiguously that Earth's rotation rate has changed dramatically over geological time, and that the planet's history is not one of stability, but of continuous slow transformation. Geology's records are, in this sense, the planet's flight recorder. Every turbulence event is logged. Every system failure leaves a mark in the strata. When a geologist reads a rock sequence, they are reading the accident report for disasters that happened long before any human civilization existed to witness them. And what those reports consistently show is that the planetary systems currently showing signs of stress have reorganized before, sometimes dramatically, always consequentially. The pole reversals did not announce themselves. There was no single moment of catastrophic change. Instead, a slow deterioration of one system created conditions that weakened others. Reduced magnetic shielding altered atmospheric chemistry. Altered atmospheric chemistry affected climate. Climate instability pressured ecosystems. Ecosystems under pressure became fragile. And then, event by event, species by species, the old equilibrium gave way to a new one. The rock record doesn't tell us how long that transition took, or what it felt like to live through it, but it tells us, with granite certainty, that it happened. If the most recent near reversal, not even a full reversal, just a temporary weakening 42,000 years ago, contributed to the extinction of a human species that had survived ice ages and continental migrations for hundreds of thousands of years. What does that suggest about where we currently stand? We treat fossils as museum pieces, curiosities, evidence of creatures that failed to survive. But fossils are not relics of the past. They are postcards from a future that hasn't arrived yet, sent by species that encountered precisely the kind of multi-system destabilization now visible in every layer of Earth science data, and didn't find a way through it. The past has issued its warning clearly and in writing, inscribed in every magnetized lava flow and every fossilized coral reef from here to the bottom of the geological record. The future is converging, and it is converging quite literally. All of these destabilizing systems, the shifting core, the weakening field, the melting ice. The wandering poles are simultaneously building pressure against the very rock beneath your feet. A 2023 study published in Geophysical Research Letters confirmed a statistical correlation between Earth's rotational velocity and the frequency of major earthquakes, specifically those registering magnitude 7 or higher on the moment magnitude scale. The pattern in the data is consistent and sobering when Earth's rotation accelerates. The rate of large seismic events increases approximately 5 to 6 years later. 5 to 6 years, which means the acceleration that began around 2020 is now loading a geological trigger that, by this analysis, would be expected to pull sometime between 2025 and 2026. Earth's crust is not a single solid shell. It is a fractured mosaic of more than 15 major tectonic plates, rigid slabs of rock averaging roughly 100 kilometers thick that float on the viscous upper mantle beneath them, continuously drifting, grinding against each other, diving beneath one another at subduction zones, and pulling apart at mid-ocean ridges. The boundaries between these plates are where the planet's structural stress is concentrated. They are the seams of the shell, and they are under load at all times. What changes is the magnitude of that load, and what it takes to push a fault that has been accumulating stress for centuries past its breaking point. Two mechanisms are now operating simultaneously, and they are pushing in the same direction. The first is rotational. As Earth's spin rate increases, the centrifugal effect at the equator changes slightly. The planet's equatorial bulge, the 21-kilometer difference between equatorial and polar radius, responds to rotational velocity. A faster spin means fractionally more outward force at the equator, which translates into changed stress distributions along plate boundaries, particularly those oriented roughly parallel to lines of latitude. The effect at any given moment is small, accumulated over years of continuous acceleration, and concentrated at boundaries already loaded to near failure. It becomes a meaningful additional force on a system where the difference between stability and rupture is measured in pascals of pressure. The second mechanism is glacial. As ice sheets in Greenland and Antarctica continue melting at the rates documented by GRACE satellite measurements, Greenland losing approximately 280 billion tons per year, Antarctica approximately 150 billion tons per year, the land beneath is relieved of an enormous compressive load. The response of the solid Earth to this unloading is called glacial isostatic adjustment. The crust, no longer pressed down by the weight of kilometers of ice, begins to rise. This rebound is not instantaneous. Rock is stiff, and the mantle beneath flows on timescales of centuries, but it is measurable and it is ongoing. In parts of Scandinavia and Canada, where the great ice sheets of the last glacial maximum have already melted, the land is still rebounding at rates of up to 1 centimeter per year, thousands of years after the ice disappeared. Imagine pressing a large, heavy stone down onto a saturated sponge. The sponge compresses. Hold it there for 10,000 years, the sponge adapts to that compressed state. The internal stresses distribute and equilibrate. Now lift the stone. The sponge doesn't spring back gently. It swells outward, the internal structure pulling apart as it expands, cracking at the weakest points. The cracks are where the fault lines are. The geological record of previous deglaciation events confirms this is not hypothetical. Studies of the period following the end of the last ice age, approximately 10,000 to 15,000 years ago, show a measurable increase in volcanic activity and large seismic events in formerly glaciated regions as the ice retreated and the crust rebounded. Iceland, sitting directly on both the mid-Atlantic ridge and a mantle hotspot, experienced dramatically elevated volcanic output during this period. The same pattern is now reasserting itself as the current warming drives ice loss at rates that are, by geological standards, essentially instantaneous. Iceland between 2021 and the present has experienced a sequence of volcanic events on the Reykjanes Peninsula, a system that had been dormant for approximately 800 years, with eruptions in 2021, 2022, 2023, and continuing into the following years, each one preceded by intense seismic swarms. This is precisely the pattern that glacial isostatic adjustment models predict for an ice-losing region experiencing crustal stress changes. In February 2023, a magnitude 7.8 earthquake struck southeastern Turkey, followed hours later by a magnitude 7.7 aftershock, a seismic sequence that killed more than 50,000 people and represented the largest earthquake in the region in more than a century. Alaska and Japan have both experienced elevated rates of aftershock activity following significant seismic events, with sequences that seismologists describe as unusually prolonged and energetically sustained. Now add the third force. The redistribution of groundwater, billions of tons pumped from underground aquifers and released into the ocean, has altered the load distribution on the crust in ways that are distinct from but compounding of the ice loss effect. Where ice loss unloads the crust at the poles, groundwater redistribution changes the load across continental interiors in regions that sit directly above some of the world's most significant fault systems: the Central Valley of California, the North China Plain, the Indo-Gangetic Plain of South Asia, all regions of massive historical groundwater extraction, all sitting in seismically complex geological environments. Three forces: rotational stress changes from accelerating spin, crustal rebound from ice unloading, load redistribution from groundwater extraction, all operating simultaneously, all exerting pressure on the same global tectonic system, none of them individually catastrophic. Together, they represent a compounding of stresses on a brittle shell that has no mechanism for gradual release, only periodic rupture. Where do you live on the seismic hazard map? Most people don't know. The map exists. The USGS publishes a detailed National Seismic Hazard Assessment for the United States, updated regularly, showing the probability of ground shaking of various intensities at every location in the country over the next 50 years, the Pacific Coast, the new Madrid seismic zone running through the central Mississippi Valley, the Wasatch Front in Utah, the Charleston Fault in South Carolina. These are all regions where the probability of significant seismic events within a human lifetime is not negligible. And the forces currently loading these systems are not the same as the forces that produced the historical record those probability estimates are based on. We worry about potholes on the highway. Meanwhile, the tectonic plates beneath are in the early stages of a stress cycle that, when it resolves, will do to certain stretches of the landscape something considerably more dramatic than potholes. And if the pressure building from below seems like enough to account for, it isn't. Because the atmosphere and the oceans are not passive observers of this process, they are active contributors, adding their own forces to the same equation at a scale that is only now becoming legible: the Atlantic Meridional Overturning Circulation. AMOC is at its weakest point in 1,600 years. And according to a 2023 study published in Nature Communications, it could collapse entirely before 2057. That date is not a distant abstraction. It falls within the expected lifetime of most people alive today. AMOC is the Atlantic Ocean's primary heat distribution system, a vast, three-dimensional circulation of water that functions like a planetary scale conveyor belt. Warm, salty surface water flows northward from the tropics along the eastern coast of North America, releasing its heat to the atmosphere and moderating the climates of Western Europe and the northeastern United States in the process. As it cools and becomes denser, It sinks in the North Atlantic, flowing southward along the ocean floor at depth, eventually upwelling in the Southern Ocean and the Indian and Pacific Oceans before warming again and completing the circuit. The full loop takes roughly 1,000 years, but its effects are immediate without AMOC. The same latitudes that currently enjoy temperate climates would experience conditions dramatically colder, drier, and more volatile. The connection between AMOC and Earth's rotational dynamics is not obvious at first, but it is real. The atmosphere and the ocean are not merely passengers on a rotating planet. They are active participants in the planet's angular momentum budget. Every shift in the jet streams, the high-altitude rivers of fast-moving air that circle the planet, transfers angular momentum between the atmosphere and the surface. Every major storm system, every El Niño and La Niña cycle, every sustained change in the trade winds exerts a torque, a rotational force, on the solid Earth below. The planet's rotation rate at any given moment reflects not just the deep interior dynamics discussed earlier, but the integrated influence of every atmospheric pressure system and every ocean current operating on its surface simultaneously. The jet streams have been documented shifting poleward and becoming more erratic as the temperature gradient between the tropics and the Arctic narrows, a consequence of the Arctic warming roughly 4 times faster than the global average. El Niño events, driven by Pacific Sea surface temperature anomalies, have been increasing in intensity. The redistribution of momentum between the atmosphere and the crust through these changing patterns is real, measurable, and contributes to the very rotational acceleration that opened this entire story. The systems are not separate, they are coupled. A 2015 study in Nature Climate Change and a 2021 study in Nature Geoscience both confirmed, through different methodological approaches, that AMOC has weakened by approximately 15% compared to its average strength during the 20th century, the largest weakening observed in the instrumental and paleoclimate record extending back 1,600 years. The 2023 study went further, identifying early warning signals in sea surface temperature patterns consistent with a system approaching a critical transition, a tipping point beyond which the circulation would shift to a fundamentally different state rather than recovering its current one. What does AMOC collapse actually look like in terms that translate from oceanography to human consequence? Northwestern Europe, including the United Kingdom, Ireland, Scandinavia, France, and Germany would experience average temperature declines of 5 to 10 degrees Celsius over the decades following collapse. This is not modest. This is the difference between the current climate of London and the climate of Reykjavik. Agricultural systems built over centuries for current conditions would face near total disruption. The Sahel region of Africa, which currently receives rainfall, partly dependent on the northward flow of warm Atlantic water, energizing the West African monsoon, would experience severe and prolonged drought. The South Asian monsoon, which sustains agriculture for more than 1 billion people across India and Bangladesh and Pakistan, would shift in timing and intensity. Sea levels along the eastern coast of North America, New York, Boston, Miami would actually rise faster than the global average because AMOC currently helps hold water back through its circulation pattern, and its collapse would allow that water to redistribute toward the shore. AMOC is, in the most functional sense, Earth's global air conditioning system. It moves thermal energy from where there is too much of it to where it can be released and redistributed. When it fails, there is no backup unit. There is no technician to call. There is no way to reboot it on a human timescale. The ocean, once shifted to a new circulation state, stays there. Recovery, if it occurs, operates on timescales of centuries to millennia. Could a change in an Atlantic Ocean current actually affect what you pay for groceries next year? Walk the chain AMOC weakens further. European grain harvests fail in consecutive cold. Wet seasons, global wheat supply contracts, commodity prices spike the cost of bread, pasta, and processed food. Rises in every market connected to the global food system, which is every market. The 2022 global food price shock, driven partly by the war in Ukraine disrupting Black Sea grain exports, demonstrated with stark clarity how fragile the supply chains connecting oceanic agricultural regions to urban consumers actually are. An AMO-driven disruption would be broader, slower in onset, and with no political resolution available. People worry about El Niño every few years, a temporary warming of the Pacific that disrupts rainfall patterns and raises food prices for a season or two before correcting itself. A MOC collapse is El Niño without a reset button and without a warranty. It is a permanent transition to a new climatic regime, arriving on a timeline that current data suggests is not centuries away, but potentially decades. All of these pressures from the core's shifting momentum, from melting ice, from weakening ocean circulation, from a destabilizing atmosphere, are now converging, not sequentially, where one would resolve before the next began, simultaneously, and they are all funneling toward the same point of maximum vulnerability, the digital civilization that humanity has constructed on the assumption that none of this would ever happen at the same time. Every power grid, every internet backbone, every financial exchange, every hospital life support system built in the modern era rests on a single hidden assumption that the planet will rotate at a constant, predictable rate forever. Not one of those systems was designed to tolerate what is currently happening. This is not an engineering oversight born of carelessness. It was a reasonable assumption for most of human history. For 4.5 billion years, the variation in Earth's rotation was slow enough, gradual enough, that building civilization around the premise of a steady 24-hour day was entirely rational. The problem is that the assumption was never written into the design explicitly. It was simply taken as given. The way architects assume gravity will continue pointing downward. And assumptions that are never explicitly stated are the ones that cause the most catastrophic failures when they turn out to be wrong. Modern digital infrastructure is synchronized to Coordinated Universal Time, UTC, at every level of its operation. Every bank transaction carries a UTC timestamp accurate to the millisecond. Every packet of data moving across the internet is tagged with timing information derived from atomic clock networks distributing UTC globally. Every smart grid controller managing the flow of electricity across a transmission network operates on synchronized time signals. Every ICU ventilator logs its cycles with timestamps. The entire architecture of the connected world is, at its foundation, a timekeeping system that happens to also move money, transmit information, and keep people alive. The power grid is the first and most immediately physical tipping point in this chain. The North American electrical grid operates at 60 Hertz, 60 complete alternating current cycles per second. This is not an arbitrary standard. The entire grid must maintain this frequency in synchrony across thousands of kilometers of transmission lines, from generating stations to substations to the outlet in your wall. Every generator connected to the grid must spin at exactly the right speed to produce current at exactly 60 Hertz. Deviation from that frequency, even fractions of a hertz sustained for more than a few seconds, triggers automatic protective systems that disconnect generators to prevent equipment damage. When enough generators disconnect simultaneously, the load on the remaining ones spikes, causing them to slow below frequency, triggering more disconnections. This is a cascade failure. It propagates faster than any human operator can respond. The Northeast blackout of 2003 is the canonical example. A software bug in an alarm system at a single utility in Ohio prevented operators from seeing that transmission lines were overloading. Over the course of about an hour and a half, The problem cascaded across the northeastern United States and into Canada, eventually cutting power to approximately 55 million people across 8 states and 2 provinces. The initiating cause was a software failure that disabled a monitoring display. The cascade did the rest. Total restoration took up to 4 days in some areas. The economic cost was estimated at between $4 billion and $10 billion. A timing synchronization failure affecting GPS, derived time signals across multiple nodes of the grid simultaneously, would be categorically worse, broader in geographic scope, faster in propagation, and with no single utility's software patch as a remediation path. The financial system is the second tipping point, and its vulnerability operates at a scale of time that most people cannot intuitively grasp. High-frequency trading now accounts for the majority of equity trading volume on major American exchanges. These systems execute transactions in microseconds, millionths of a second, and their entire operational logic depends on the ability to establish, with certainty, the sequence of events. Which order arrived first? Which price was valid at which moment? Which trade preceded which other trade by how many nanoseconds? Regulatory frameworks governing market fairness are built on the premise that timestamps are accurate and universal across all participants. A 1 millisecond discrepancy, 1,000th of a second, between 2 trading systems interpreting a moment differently is sufficient to create phantom arbitrage opportunities, trigger circuit breakers, and in the worst case, generate the self-reinforcing cell spiral characteristic of a flash crash. The 2010 flash crash saw the Dow Jones Industrial Average drop nearly 1,000 points in minutes. Its cause was a single large algorithmic trade interacting unexpectedly with market microstructure. A global timestamp anomaly would hit every participant simultaneously, on every exchange, with no warning and no coordinated response protocol in existence. The third tipping point sits in every hospital intensive care unit in the country. ICU ventilators, infusion pumps, cardiac monitors, and automated medication dispensing systems all operate on precise timing cycles and log every intervention with timestamps accurate to the second or better. These logs are not merely administrative records. They are the mechanism by which clinical staff verify that patients received correct medication doses at correct intervals, that ventilator settings were adjusted at the right moments, that alarms triggered within required response windows. When timing systems malfunction, these logs become unreliable. Automated systems making decisions based on timing a pump that releases a drug at precisely calculated intervals. A ventilator that adjusts pressure based on a timed breathing cycle can act on incorrect timing data without triggering an error flag, because the system has no independent way to verify that its sense of time is correct. The failure mode is silent. The consequences are not. The fourth tipping point is the communications infrastructure that binds the other 3 together. Fifth-generation wireless networks 5G depend on GPS-derived timing for a function called network synchronization. Unlike earlier cellular generations, 5G's architecture requires base stations to synchronize their transmissions to within a few hundred nanoseconds of each other to manage the way signals are split, directed, and reassembled. This synchronization is provided by GPS timing receivers embedded in every base station. If GPS timing accuracy degrades, whether from rotational anomalies affecting satellite geometry, from increased error rates in the positioning system, or from a timing discontinuity introduced by a negative leap, second 5G network performance degrades with it. In areas of dense deployment, where base stations are closely spaced and interference management is most critical, timing errors produce dropped connections, reduced throughput, and in severe cases, interference cascades that take portions of the network offline. The entire structure of modern digital civilization rests on a clock. Not metaphorically, literally. A distributed, atomic, globally synchronized clock. And that clock is now being asked to track a planet that is no longer behaving the way the clock was calibrated to expect. Imagine building a skyscraper on a foundation that everyone agreed was solid. Then the ground begins moving, not dramatically, not enough that you'd notice standing on the street outside, but enough that precision instruments in the basement register a continuous, slowly accelerating drift. The building itself appears fine, the lobby looks normal, the elevators run, but deep in the structural engineering, load distributions are shifting away from design parameters. The safety margins built into the design were not sized for a moving foundation. They were sized for a static one. How many days could you sustain yourself if the power grid and internet failed simultaneously? No electricity, no running water, which depends on electric pumps, no functioning ATM or point-of-sale system, no GPS navigation, no cellular communication, no supply chain restocking of any store you could reach on foot. Most Americans have less than 3 days of food at home and no reliable access to water without municipal infrastructure. The systems we've built are not just convenient. They are the precondition of survival for the population density of modern cities. We spent years worried about artificial intelligence seizing control of critical infrastructure. It turns out the actual threat is the planet quietly deciding to change its own time zone without asking anyone's permission, and the entire digital civilization discovering, too late, that it never thought to design for that possibility. And the most frightening part of all of this is not any single system's vulnerability. It's that none of these are separate problems. They are resonating simultaneously, feeding into each other, all moving toward a threshold that systems science calls a tipping point, and once crossed, there is no path back to where we started. For the first time in the history of organized science, researchers across 16 distinct disciplines, climatology, geophysics, oceanography, geomagnetism, glaciology, seismology, geodesy, atmospheric science, and others are simultaneously reporting anomalies in their respective domains. And every one of those reports carries the same timestamp, the 2020s, not the 1980s, not the turn of the millennium. This decade. To understand why the simultaneity matters more than any individual finding, you need the concept of tipping points as systems. Science actually defines it not as metaphor, but as a precise mathematical description of how complex systems behave near critical thresholds. A tipping point is the state at which a system that has been responding gradually and reversibly to external pressure crosses into a regime where the response becomes self-reinforcing and irreversible. The system doesn't just change, it reorganizes into a fundamentally different state and stays there, even if the original pressure is removed. The classic physical analogy is a ball balanced on top of a hill. Push it slightly, and it rolls back to center. The system is resilient. Push it past the crest, and it rolls down the other side regardless of what you do next. The tipping point is the crest, and once past it, the direction is determined. Now take inventory of where things stand, drawing only on peer-reviewed findings published between 2020 and 2024. The inner core has reversed its rotation direction relative to the surface, a finding confirmed in Nature Geoscience in 2023. With the reversal estimated to follow a cycle of approximately 70 years, whose current phase is transferring angular momentum outward to the crust. The outer core has shown anomalous changes in its convective flow patterns, documented through swarm satellite magnetic field data in the same year. Earth's magnetic field has weakened 9% since 1840, and the South Atlantic anomaly is expanding and developing a second center of weakness, per European Space Agency data published in 2020. Earth's rotational velocity has been breaking records for shortest days since 2020, a sustained multi-year acceleration unprecedented in the atomic clock era. The geographic poles have shifted approximately 4 meters since 1990, driven by ice melt and groundwater redistribution, confirmed by NASA in 2023. The Chandler wobble suppressed to near zero amplitude between 2017 and 2020, an event without satisfactory explanation in the literature. Polar ice loss continues at rates that GRACE satellite measurements confirm are accelerating in both Greenland and Antarctica. AMOC has weakened 15% below its 20th century average and is showing early warning signals of critical transition. Per Nature Communications 2023, tectonic activity is elevated, with the Reykjanes Peninsula in Iceland producing its first eruption sequence in 800 years, and major seismic events continuing at elevated rates across tectonically active regions. 9 confirmed anomalies, 9 different measurement systems, 9 independent lines of evidence, all flashing amber or red in the same decade. The instinct, when presented with this list, is to process each item separately. The inner core problem, the magnetic field problem, the ice problem, the AMOC problem, as though they were unrelated headlines from different sections of a science journal. That instinct is wrong, and it is the most dangerous way to interpret what the data is saying. These are not 9 independent problems. They are 9 links in a single feedback network that is currently amplifying itself. Ice melts, mass redistributes, axis shifts, rotational dynamics, change core coupling adjusts. Magnetic field structure responds, more ice melts because altered atmospheric circulation from AMOC weakening reduces cooling in polar regions. More mass redistributes, the axis shifts further. The cycle doesn't need an external accelerant to intensify. Once it reaches sufficient momentum, it drives itself. Each perturbation feeds the next. The resonance builds not because any single component is catastrophically broken, but because all of them are pushing simultaneously in directions that reinforce each other. Think of a symphony orchestra tuning before a performance. Each musician adjusts slightly off their correct pitch, not dramatically, not enough to notice individually, but when the conductor raises the baton and every instrument begins playing at once, each one slightly wrong in a way that compounds with the others, the result is not music that is slightly out of tune. It is cacophony. The problem was not any single instrument. It was the system of instruments acting together. The IPCC 6th Assessment Report, the most comprehensive synthesis of climate and Earth system science ever assembled, published between 2021 and 2022, introduced the concept of cascading tipping points into its formal language for the first time. Specifically, the report acknowledged the possibility that crossing one tipping point could reduce the threshold for crossing others, that the tipping points are not independent, but coupled, capable of triggering each other in sequence like dominoes, but dominoes where each falling piece actively destabilizes the next before it even begins to fall. This was not fringe science appended to the report as speculation. It was a formal finding of the working groups, reflecting a shift in the scientific consensus from treating planetary systems as parallel but separate to recognizing that they form a coupled, interacting network. If 9 systems are simultaneously approaching their limits, where are we on the curve? Dynamical systems theory has a precise answer for systems near tipping points. The approach is characterized by what is called critical slowing down. As a system nears its threshold, it loses the ability to recover quickly from small perturbations. It takes longer to return to equilibrium after each disturbance. The fluctuations become larger and more erratic. These signatures slowing recovery rates, increasing variance are detectable in the data before the tipping point itself is crossed, which is why scientists look for them as early warning indicators. Multiple Earth systems currently show these signatures simultaneously. Humanity has survived ice ages that buried continental interiors under kilometers of ice. It has survived the Chicxulub asteroid impact that terminated the Cretaceous period. It has survived Toba, the supervolcanic eruption 74,000 years ago that may have reduced the total human population to a few thousand individuals. It has survived plague, famine, and 2 world wars. We are a resilient species with a remarkable track record of endurance against catastrophic odds. But in every one of those previous crises, the crisis was singular. One catastrophic event, one system under stress. The species adapted, suffered, and eventually stabilized. We have never before faced 9 coupled planetary systems simultaneously approaching critical thresholds, while also managing a digital civilization whose entire operating logic assumes those systems will remain stable. That combination has no historical precedent, and therefore no historical template for what comes next. You've heard everything that is currently happening to Earth. The days are shorter, the clocks are drifting, the satellites are losing their grip, the core has reversed, the poles have moved, the shield is tearing, the ocean conveyor is failing, the ground is loading for release. But there is one final truth larger than all of it, larger than anything presented so far that most people, including most scientists, have not yet been willing to look at directly. Throughout everything presented in the preceding 14 parts, there has been an unspoken assumption embedded in every sentence, a frame so natural, so intuitively obvious, that neither the telling nor the listening questioned it for a moment. The assumption is, this something is wrong with Earth. The planet is unstable. It is behaving abnormally. It need, in some sense, to be fixed. That assumption is false. And recognizing why it's false doesn't make any of the data less alarming. It makes the situation considerably more so. Earth is not breaking. Earth is self-correcting exactly as it has done for 4.5 billion years. Every anomaly documented in this story, every record broken, every system showing stress, every measurement trending in an unexpected direction, all of it falls within the range of behavior this planet has exhibited repeatedly throughout its geological history. The inner core reversing its rotation, it has done this before, on a roughly 70-year cycle, for as long as it has existed. The magnetic field weakening and the poles drifting, it has done this 183 times in the past 83 million years alone. The rotation rate changing, the axis shifting, the ocean circulation reorganizing the rock record, the coral record, the ice core record. All of them contain the signatures of these same processes, playing out over and over across deep time. What we are witnessing is not a malfunction. It is a recalibration. The planet is doing what planets do, redistributing energy, transferring momentum between its layers, seeking a new equilibrium after perturbations have accumulated beyond what the current configuration can sustain. The timescales feel alarming from a human perspective because they are playing out within a single human lifetime. From Earth's perspective, this is a routine adjustment, a breath between longer, slower rhythms. The genuinely terrifying truth is not that Earth is broken. It is that Earth has survived everything. 5 mass extinction events, each one erasing the majority of species alive at the time. The Chicxulub asteroid impact 66 million years ago, a rock approximately 10 kilometers wide, striking the Yucatan Peninsula and releasing energy equivalent to roughly 1 billion nuclear weapons simultaneously, triggering firestorms, a years-long impact winter, and the collapse of food chains globally. Snowball Earth at least 2 episodes, the most severe approximately 700 million years ago, during which the entire planet froze from poles to equator, ocean surfaces locked under kilometers of ice, the surface temperatures averaging -50 degrees Celsius. The conditions remaining for millions of years before volcanic outgassing eventually broke the freeze. Magnetic field collapses during geomagnetic reversals that left the surface exposed to the full intensity of the space environment for thousands of years at a stretch. Supervolcanic eruptions that injected enough material into the atmosphere to alter global climate for decades. Every single time, Earth absorbed the event, reorganized its systems, and continued rotating. It found a new equilibrium different from the previous one, sometimes radically so, but stable in its own terms. The planet's 4.5 billion year track record on this point is, quite literally, perfect. The one thing that was never present during any of those previous adjustment cycles, not during any of the 5 mass extinctions, not during Snowball Earth, not during any magnetic reversal in the geological record, is 8 billion human beings operating 400 GPS satellites, a global internet running on synchronized atomic time, financial systems processing trillions of dollars of transactions per day, and a food distribution network that can feed dense urban populations only as long as the supply chain operates within its design parameters. All of that infrastructure was engineered, optimized, and deployed during one of the most geologically stable periods in Earth's recent history. The 250 years of industrialization that produced it coincided with an era of unusual climatic and geophysical stability, stable enough that engineers could safely assume the ground wouldn't shift the coordinate systems, that the day length was constant, that the magnetic poles were where the charts said they were, that the ocean currents would continue distributing heat the way they always had. Those were reasonable assumptions for that period. They are becoming less reasonable with each passing year. The real question, the only question that ultimately matters, is not whether Earth is going to be all right. Earth will be all right. That answer is not in doubt. The question is whether human civilization is flexible enough to survive a routine planetary adjustment cycle when every system it depends on was optimized for a world that doesn't change. That question has never been asked before, because the combination of technological dependence and planetary instability has never existed simultaneously before. Previous civilizations that faced geophysical disruption, the Bronze Age collapse, the fall of the classic Maya, the societal disruptions associated with the Toba eruption, operated at population densities and technological complexities orders of magnitude lower than the present. They had more room to absorb disruption, more redundancy built into their simpler systems, less catastrophic interdependency between their infrastructure nodes. When a Bronze Age grain store failed, the disaster was local. When the global timing infrastructure of the 21st century fails, the cascade is planetary and simultaneous. And now the final layer, the one that reframes everything else. What is happening to Earth's rotation, its magnetic field, its core dynamics. These anomalies are not confined to Earth. Mars has been showing anomalous dust storm behavior and atmospheric changes that planetary scientists describe as outside the range of prior observations. Jupiter's Great Red Spot. The centuries-old storm system, large enough to swallow Earth, has been shrinking and changing structure in ways that remain poorly understood. The Sun's magnetic activity, measured through sunspot cycles, is entering solar cycle 25 with an intensity that exceeded the predictions of the forecasting panel convened by NASA and NOAA. The cycle is running hotter and more active than the consensus model projected. Multiple planets across the solar system have shown measurable changes in their magnetic environments within the same time window in which Earth's anomalies have accelerated. At the legitimate edges of heliospheric physics, not in fringe publications, but in peer-reviewed journals examining the Sun's interaction with its surrounding interstellar medium, there is an active and unresolved scientific question about whether the solar system has entered a region of the local interstellar medium with different plasma density characteristics than the region it occupied during the 20th century. The heliosphere, the vast bubble of solar wind that encloses the solar system and shields it from galactic cosmic rays, has a structure that responds to the density of the interstellar medium through which the Sun moves. The Sun moves through the galaxy at approximately 20 kilometers per second. The local interstellar medium is not uniform. If the solar system has drifted into a denser region of interstellar plasma, the heliosphere's structure changes. The cosmic ray flux entering the inner solar system changes. The space environment experienced by every planet changes simultaneously. No scientific consensus has formed around this hypothesis. The data is preliminary. The mechanisms are complex. Some researchers in heliospheric physics consider it seriously. Others regard it as unproven. What is true is that it cannot be dismissed on the basis of current evidence, and that it would provide a single unified explanation for the otherwise puzzling simultaneity of anomalies across multiple planetary bodies. Nobody knows. The honest answer, at the frontier of what humans currently understand about the solar system's relationship with the galaxy around it, is that the data is waiting for someone to ask exactly the right question. Earth is not crying out. It is breathing the same 4.5 billion year breath it has always drawn, slow and vast and completely indifferent to the civilizations that happen to be present during any particular exhale. The planet will survive this. That conclusion is not in question. The question is what fits inside the space between one breath and the next. Between the inhale and the exhale of a planetary adjustment cycle, there is a window. For previous forms of life, that window didn't require power grids or GPS or synchronized financial systems or precisely timed ICU equipment. They needed food, water, shelter, and enough genetic diversity to adapt. The window was wide enough for biology to work in. Our window is narrower, not because the planet is changing more dramatically than before, it isn't, but because everything we have built to sustain 8 billion lives operates within tolerances that the planet, in its current moment of recalibration, is beginning to exceed. Whether human civilization is flexible enough to compress itself through that narrowing window before it closes, that is the question no geological record can answer. Because nothing like us has ever been here before when this happened. Earth will keep rotating when this is over. Whether we are still on it to notice is the only variable that remains genuinely open.